Okay, in this video we're going to look at how the SPCS operates and compare it to conventional operation looking at a system head curve. Now in the example you see here, this is a slightly different pump. It's 1125 gallons per minute at 68 feet. And at that point we know how to read a curve, so we just basically go straight up, we cross that line, we go to the left, and we see that that's about 24 horsepower. So this is our basic pump, and that's our design point we've selected. Now this is a multi-speed curve, and we've chosen this type of a curve because it will represent what the SPCS is actually doing better than a curve with varying diameters on it. So as we look at the next image, we've overlaid now onto the system curve a couple of more lines. The conventional operating method is an uncontrolled single speed. So this red heavy line is the range of operation from a clean system back up to the system design point. The pump will operate on this line depending on the load given to it from the filter. And then the horsepower that the conventional system will draw is represented up here on this red line at 1187 RPM. So in looking at this, we see that once they clean the filter, the conventional system is going to want to operate out here because of the reduced restriction to flow, because the clean filter is a lot freer flowing. That looks like it's close to 1,850 gallons per minute, and the head has dropped down to maybe 54, and the horsepower has jumped up from the 23 or so all the way up to probably close to 29. The conventional system will then operate at this point, and we know because it is a sand filter system, it's going to operate at this low restriction area for quite a while until it starts to gather enough debris to close the gaps and start to increase the resistance to flow. Once it does that, the conventional system over time will gradually move to the left and up until it finally reaches the system design point. At that point, the operator will backwash the filter and send us back into this area. So you can see that over typical use, there's going to be a lot of time spent on a conventional system in this area of the performance curve. Represented up here in the horsepower, you can see that it's a significant increase in horsepower from what the motor is designed to do. And it only sees this design point just before it is backwashed. So now the SPCS comes into play, and why does the SPCS work so well at saving energy? Because the SPCS is always looking at the flow and matching the pump's performance to the resistance or the load in the system. So when the filter is clean, the resistance is low, the SPCS will cause the unit to go slower in RPM, reducing its performance down to the 950 RPM curve at about 40 feet when the filter's clean. And then as the filter works its way up, it will gradually increase the speed. You can see it goes up to 1,068 and then finally 1187 until it reaches the design point where the system is backwashed and brings us back down here. Now the thing about the SPCS is we operate in a vertical, straight up and down. We keep the efficiency of the design point as we slow down. That means that the pump is operating at its most efficient point at every point along this curve, straight up and down. And you can see up here, represented by the green line, the horsepower goes from the design point of about 23 all the way down to about 12-ish, give or take. And we know, again, that the filter spends a larger amount of time in this clean area than it does in the system design area. So the SPCS saves a substantial amount of energy. The SPCS also has the ability to operate at a different speed at night, represented by these two violet colored lines. In the nighttime mode, the SPCS will need to deliver just enough flow to keep the heater from tripping on a low flow and keep the chemical system from tripping on a low flow. That exact flow rate is determined at the site because the piping and arrangement and the location of all these things is different. So this one is just an estimation of where it's at. But again, during the nighttime mode, when the heater is calling for heat, this is the range that the SPCS can operate through. Considerably less horsepower than even in the normal range for the SPCS. And then at times during the night, the heater will not be looking for any heat. The pool covers will keep it in and the heater may just be able to turn off, in which case we can drop the flow even further, just barely enough to keep the chemical system happy and reduce the flow even more. So this comes into a savings on this particular pump of about 47% of the energy expended. So how does that work? How do those numbers work? Let's take a quick look at the formulas. And the basic formula we always look at is GPM times TDH over 3960. That gives us what is referred to as a theoretical horsepower. Theoretical horsepower gets converted into what we refer to as brake horsepower by adding in the pump efficiency. So you can see that the conventional system will increase the GPM significantly while the TDH comes down a little bit. That formula translated down to this last one, we calculate how much we're spending. Again, there's a constant factor from the formula. Then there's the GPM, the TDH, how much we pay. We plug in the pump and motor efficiencies. That gives us a dollar amount per hour for pumping. So you can see that the SPCS is going to lower both the GPM and the TDH, making the number on the top of this formula smaller. When that number gets smaller, the overall number gets smaller. So that's how the SPCS saves energy and how it works when compared to a conventional control system.